Back from spring break, an extended spring break. Today we're going to be discussing a variation of parameters. So this is the other method we discussed from last time when we talked about the method of undetermined coefficients to discover solutions to differential equations of the second order. Now we're going to discuss another method that's more general that can be applied to a far greater range of problems with a technique that's called the variation of parameters. So just like last time, we're going to go through the derivation first to show you how the method works in principle, and then how we can apply it to several examples. Now, just so you guys know, and so you know what to expect in each of these different sessions, I'm expecting each of these videos to be approximately 10 minutes long. That doesn't mean you only get one video for 10 minutes. Each session should be a series of 9 10-minute instructional videos, so overall an hour and a half. So it's no different than the 3 hours of class time that you would get normally during the week. So expect 9 videos that are each 10 minutes long. Each of these will be uploaded onto YouTube, so you can get a sense of how to obtain access to these videos. I will also post them on Blackboard. In addition, all the notes that you see me drawing and writing during these videos and during these instructional sessions, I will post on Blackboard as well for you to review. So you can feel free to sit back and relax and watch me take notes, but what I would highly recommend for each of you to do would be to sit down with your pen and with your paper in hand and take notes along with me. It'll help you to retain every single step and also help you and challenge you to follow along. For those of you that don't need to do so at your own leisure. So without any more being said, let's go ahead and get started. So, like we said before, in the last section we looked at the method of undetermined coefficients for finding a particular solution to the following problem. It was P of t, y, double prime, this is what makes it second order, plus q of t times y prime, plus r of t times y equals some function g of t, okay? And throughout this lecture, I'm going to call this, all of this up here, equation 1, okay? Just so you know what we're referencing as we go on, okay? And we saw that while it reduced things down to just an algebra problem, that algebra could become quite messy. And on top of that, undetermined coefficients will only work for a fairly small class of functions. So to resolve this, the method of variation of parameters is much more general and can be used in many more cases. However, there are two disadvantages to the method. First, and let me go ahead and write this down. First, the complementary solution okay? The complementary solution, and I'll just abbreviate here, is absolutely required, or I'll just say is required, to do the problem. This is the first disadvantage, okay? The second disadvantage was in order to complete this method, we'll be doing a couple of integrals, and there is no guarantee that we will be able to do the integrals. So we'll be doing a couple of integrands here and there, and these integrands might be intractable. Meaning there's no analytical way to solve them, and you would have to resort to numerical methods to solve those solutions. So I will present a few examples where we may have intractable integrals, but overall, generally speaking, this method works just fine for most cases and for most problems. Okay. So I should also mention that while it is possible to write down a formula to get the particular solution, we may not be able to actually find it if the integrals are too difficult, or if we are unable to find the complementary solution. So that's a nice tie-in to these two disadvantages that you see here written down for you. Okay, so with the remaining 5 minutes for this video, we're going to derive the formula for variation of parameters, and we'll start off by acknowledging that the complementary solution to 1 is given by the following. So, number of complementary solutions are written like this, y sub c of t, and that's going to be set equal to c1 y1 of t plus c2 y2 of t. Okay, so that's the complementary solution that we're going to be addressing. And this is the complementary solution to equation 1 above. Remember, equation 1 was listed up here. So this is the complementary solution to 1. So next, remember as well that this is the general solution to the homogeneous differential equation. Okay, and that would be this equation. P of t y double prime plus q of t times y prime plus r of t, okay, times y, which equals 0. And we'll call this equation 2. Okay. Also, recall that in order to write down the complementary solution, we know that y sub 1 of t and y sub 2 of t are a fundamental set of solutions. Okay, that's important to remember. And what we're going to see, and what we're going to do, is if we can find a pair of functions, u1 of t, make sure it looks like a u, and u2 of t, so that we have the following particular solution. Remember, that's capital Y subcapital P of t, which equals u sub 1 of t times y sub 1 of t plus u sub 2 of t times y sub 2 of t. Okay, so that's the form that we're going after with variation of parameters with respect to the particular solution. And this, in general, will be a solution to equation 1 that we wrote up above before. Okay? All right. So then to end this video, what I wanted to now is just discuss what's going on. We have two unknowns here. Okay, so these are the two unknowns. And so we'll need two equations eventually. One equation is easy. Our proposed solution must satisfy the differential equation. So we'll get the first equation by plugging our proposed solution into equation 1. That'll be the first step. The second equation can come from a variety of places. We are going to get our second equation simply by making an assumption that will make our work easier, and we'll say more about this shortly in the next video. Stay tuned.